In this video, we'll talk about continuous growth or decay and Euler's number. Now, if you haven't checked out the compound interest video, I highly suggest you do that first, as a lot of that information is very vital to understanding this concept. So let's dive right into the formula. So, in a lot of ways, continuous growth can be easier than non-continuous growth, I guess. So our letters are very similar. The only difference is that we have this E here, and this is not a variable. This is Euler's number. So it turns out that if we were to run n, and remember n in the compound interest formula is how many times we compound something. So if something is continuously growing, not by the second, not by the nanosecond, continuously growing, which is pretty common. You'll look at population and those kind of things, radioactive decay, you see this continuous thing. Things are continuously growing or decaying depending on what you're looking at. So Euler's number is roughly 2.71. It's irrational. It keeps going. It doesn't repeat. And it's this idea of if I took n and cranked it to infinity, this is the number that it would approach. As I increased n to a certain value, that would be the base of my exponential function. So in this case, A, P, R, and T are the same as they are in the compound formula, or the compound interest formula. And we'll just go through that really quick. So A is the initial amount. P is your, A is your ending amount. I'm going to change the arrows there. So, apologies for the confusion here. P is your initial. A is your end, amount at the end. R is your growth rate or decay rate. And decay rate would be negative, so just be very cautious of that. And T is time. And usually we talk about years, but sometimes when we're talking about growth of population or radioactive decay, we might be talking about more or less depending on what kind of units we need to deal with. So as long as R and T have the same kind of units, so if R is an annual rate, then T has to be in years. If R is a minutely rate, then T has to be in minutes, those kind of things. So just be cautious. So long as R and T are of the same units in terms of time, then you can call T or time whatever it is in terms of units. So let's dive right into an example. Again, we're reading through and we're just picking out some important information. There's 10 bacteria, it's growing on a dish, and it's growing continuously. Now this tells me I'm going to use Euler's number. That's the tip-off. If it's continuous, it will say so. There's 30% each hour, and I want to know how much is going to be at the end of one day. Now again, I'm going to make my list. I have P, I have A, I have R, and I have T. Okay, so in this case, P is 10. That's how much I have to start with. I don't know A. I want to know what happens at the end. R is 30% or 0.3. And after one day, now remember, I have to make them agree. So if R is in hours, T's also got to be in hours. So instead of one day, I'm going to write 24 hours. I'm just going to make the conversion. And then we run to our formula. So A is going to equal P times E to the power of 0.3 times 24. Now there is an E button on the calculator that you can use. You'll have to hit second and then the natural log button is what it is on TI-84s. Oh, and I guess this P should be a 10. So we're going to simplify a little bit. So we're going to take E to the power of 0.3 times 24. And if you do that, you get roughly 1,339 and some change. And then if we multiply that by 10, it's going to move the decimal over one spot. So we'll have 1,339, well, actually 13,394. Forgot to move the decimal over a touch. 0.30764. Now this is slightly different than what we did the last time we did this with the compound formula, And similar kind of thinking, we're just going to go with the whole bacteria. We're not going to worry about the chunk here. We have 13,394 bacteria. This allows for a much quicker growth rate. It's also much more realistic for so many different problems, especially if we're talking radioactive decay. So if you have a negative growth rate, you actually have, you're losing amounts as you go. It's very, very useful. It's probably more useful than the compound interest formula. We just see the compound interest formula a lot because of finances and those kinds of things. So that's continuous growth. In a lot of ways, it's actually easier than compound.